Another mathematical result of string theory is that the theory only makes sense in a world with more than 3 space dimensions. Our universe has 3 dimensions of space: left/right, up/down, and front/back. 2 possible explanations currently exist for the location of the extra dimensions. 1. The extra space dimensions, generally 6 of them, are curled up, compactified, in string theory terminology, to incredibly small sizes, so we never perceive them. 2. We are stuck on a 3-dimensional brane, and the extra dimensions extend off of it and are inaccessible to us. A major area of research among string theorists is on mathematical models of how these extra dimensions could be related to our own. Some of these recent results have predicted that scientists may soon be able to detect these extra dimensions, if they exist, in upcoming experiments, because they may be larger than previously expected. One of the major goals of current string theory research is to construct a solution of string theory that contains the particles that actually exist in our universe. A major area of research among string theorists is on mathematical models of how these extra dimensions could be related to our own. Some of these string theories started out as a theory to explain particles, such as hadrons, as the different higher vibrational modes of a string. In most current formulations of string theory, the matter observed in our universe comes from the lowest energy vibrations of strings and branes. The higher energy vibrations represent more energetic particles that don't currently exist in our universe. The mass of these fundamental particles comes from the ways that these string and branes are wrapped in the extra dimensions that are compactified within the theory, in ways that are rather messy and detailed. For an example, consider a simplified case where the extra dimensions are curled up in the shape of a donut, called a torus by mathematicians and physicists. A string has 2 ways to wrap once around this shape. 1. A short loop around the tube, through the middle of the donut. 2. A long loop wrapping around the entire length of the donut, like a string wraps around a yo-yo. The short loop would be a lighter particle, while the long loop is a heavier particle. As you wrap strings around the torus-shaped compactified dimensions, you get new particles with different masses. One of the major reasons that string theory has caught on is that this idea, that length translates into mass, is so straightforward and elegant. The compactified dimensions in string theory are much more elaborate than a simple torus, but they work the same way in principle. It's even possible, though harder to visualize, for a string to wrap in both directions simultaneously, which would, again, give yet another particle with yet another mass. Branes can also wrap around extra dimensions, creating even more possibilities. In many versions of string theory, the extra dimensions of space are compactified into a very tiny size, so they're unobservable to our current technology. Trying to look at space smaller than this compactified size would provide results that don't match our understanding of spacetime. One of string theory's major obstacles is attempting to figure out how spacetime can emerge from the theory. As a rule, though, string theory is built upon Einstein's notion of spacetime. Einstein's theory has 3 space dimensions and 1 time dimension. String theory predicts a few more space dimensions but doesn't change the fundamental rules of the game all that much, at least at low energies.